Okay, so for Unit 2, we begin the process of looking for patterns and making statements that we believe to be true from these patterns. And this is called using inductive reasoning. So inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. So if we look at these two patterns, when we wanted to make a statement that's true about these patterns, well, we have specific cases that show that it's going to continue in this direction. So if you look at this first example, you can see that it's the months of the year, just skipping every month. So after May, we would have June followed by July, and then we would skip August and have September. So from these specific cases, we can reason that this pattern is going to continue skipping a month for the rest of the year. For this specific pattern, we can assume that it's going to continue increasing by 7, 35, and 42. When several examples form a pattern and you assume the pattern is going to continue, that is you applying your inductive reasoning. And a statement that we believe to be true, we've yet to make a statement about these patterns, but we will down below. A statement you believe to be true based on your inductive reasoning is called a conjecture. Okay, so let's go practice making some conjectures about these statements after we provide some evidence. Let's try A and C together, and then you can try B and D on your own. The sum of two positive numbers. Well, we need to provide some evidence, so we can just start adding any positive numbers that you would like. 2 and 7, 3 and 5, 11 and 15. Okay. Hopefully you notice that every time you add two positive numbers, you're just going to get a positive number. You'll never have a negative. So the sum of two positive numbers is a positive, or let's say is always positive. And you have plenty of evidence down below. All right, let's try another. The number of segments formed by n collinear points. All right, let's start with 1 point. If we have 1 point, then we don't have any segments, so that would be 0. When we have 2 collinear points, we have 1 segment. When we have 3 collinear points, we have 1, 2. So we have 1 segment here, we have 1 segment here, and then we have the whole segment, so 3 total segments. For 4, you can start seeing the pattern. We have 1, 2, 3, and then we have 1 segment here, 1 segment here, so 3, 4, 5, and then the whole segment for a total of 6. Okay, and it might be tough to see right now, but if you break it up into the smaller segments, here we had 0 for 1, there was only 1 possible segment. If you break it up, we had 2 plus the larger segment of 1. Then for 4 collinear points, we had 1, 2, 3, plus these 2 larger segments, followed by the longest segment of them all. 2 plus 1, 3 plus 2 plus 1, and then maybe you can guess without drawing for 5 collinear points. Continuing this pattern, 4 plus 3 plus 2 plus 1 would be a total of 10 segments. So then we would say the number of segments formed by n collinear points is the sum of the positive, or the sum of consecutive positive integers less than n. And hopefully you can see that here. N standing for the number of collinear points. So if we had 4 collinear points, it's going to be the sum of the consecutive positive integers less than n. 3 plus 2 plus 1. For 5, 4 plus 3 plus 2, 3 plus 2 plus 1. Okay. All right, why don't you guys try to provide some evidence for B and D, and then see if you can come up with a conjecture. So remember, for B, the product of an even number and an odd number, anything that comes in mind. 4 times 3 gets you 12, an even times an odd, right? List out plenty of more examples there to provide evidence before you make your statement about something you believe to be true. For D, n for this, a rule in terms of n for the sum of the first n odd positive integers. Let me help you get started with that one. 1 is your first odd positive integer. Integers are whole numbers. Then your next integer or odd positive integer would be 3. So 1 gets you 1, 3 plus 1 gets you 4, 1 plus 3 plus 5, 1 plus 3 plus 5 plus 7. See if you guys notice a pattern about this, a rule in terms of n about the sum of the first n positive integers. Okay, for B, hopefully you notice that anytime you multiplied an even times an odd, you were always going to get an even number. It's always even, and you have plenty of evidence down here. Your evidence does not have to match mine. For D, if we continue this pattern, 9, 16, 1 plus 3 plus 5 plus 7 plus 9, we got you 25. Hopefully you notice that the sum of the first odd positive integers is always going to be a perfect square. And if we want to write the rule in terms of n, well, here n is 1, here n is 2, here n is 3, so really the sum was just n squared. We don't need our parentheses, right? So then if you plugged in, say, 3 for the first 3 odd positive integers, you get 3 squared, which gets you 9. Just check in and make sure that that statement's true. Okay, great. Let's continue with some counterexamples. To show a conjecture is true, you must prove it, which is what we were doing up above, providing evidence. If we want to show a conjecture is false, you just need one example that shows the conjecture is not true, and that would be called a counter example. Okay. So let's go practice now doing kind of the opposite, statements that are going to be false, and we just need to provide one counter example. So we'll do A together. Let's try D together and E as well, and then we'll let you try the other 3 on your own. A states the radius of every planet in the solar system is less than 50,000 kilometers. Well, here you're given planets' diameters, and we know that radius is half the diameter. So we're really looking for, if the radius is 500,000, then the diameter would be 100,000. So we're looking for any planet on here that has a diameter greater than 100,000, and hopefully you see there's obviously 2 on there, Jupiter and Saturn. So you can just pick one. Jupiter is a counterexample. That conjecture is false. How about for D? D states for any number n, negative n will always be less than positive n. Well, this is true, except if you had, and you really just want to try guess and check here, if you had a negative, right? Say you had negative 4, and we plugged in negative 4 everywhere we see n. Well, a negative times a negative, we know, becomes a positive. So this negative 4 gets us 4 is less than negative 4. That's not true. 4 is greater than negative 4. Any negative integer would have been a counterexample here. How about for E? 3 points on a plane always form a triangle. Well, here's a plane. If we had 3 points on here, they'll definitely form a triangle unless those 3 points were forming a straight line. Then we would not have a triangle, so we would say false. 3 points can be collinear. All right. Great. Okay, so let's have you try providing a counterexample for B. B says the monthly high temperature in Abilene is never above 109. Find an example in this table that shows that that conjecture is false. Hopefully you noticed that in July, the monthly high temperature was 110 degrees. That's greater than 109. That would prove that that conjecture is false. That's a counterexample. Go ahead and try C. 2 complementary angles are not congruent. We need an example of when 2 complementary angles are congruent. Okay, hopefully you remember that for complementary angles, 2 angles that add up to 90 degrees. So what 2 angles have the same measure that add up to 90 to show that this is not true? Well, you can have 2 angles whose measures are 45 degrees. 45 plus 45 gets you 90. They're congruent because those 2 angles have a measure of 45 degrees. Congruent angles have the same measure. All right, last but not least, for F, for any real number, x, that number squared will be greater than or equal to that original number. Well, this says any real number. So what if we tried a fraction? What if we tried 1/2? Right? Remember, when you plug in 1/2 and you're squaring, you're multiplying a fraction times a fraction, that number is going to get smaller. It's not going to get larger. So 1/2 times 1/2 gets us a quarter, and a quarter is not greater than or equal to 1/2. This is not true. So false, any fraction less than 1 would work here. Okay. And really, just to sum up everything we practiced in this section, the process for inductive reasoning is you are looking for a pattern. Then you are making a conjecture about that pattern. Remember, a conjecture is a statement that you believe to be true. And then you need to prove the conjecture or provide evidence of the conjecture or a counterexample that shows it's not true. Okay. You'll have practice on the homework tonight doing both, where you're making conjectures and proving conjectures are false. And then we will practice this some more in class later this week. Okay, good luck on your homework.